Hello students, welcome to Sarasa classes. Today we are discussing optical rotation. Now I have over here shown two crystal forms which I'm calling them as A and B, and say these are crystals of quartz or sodium, potassium tartarate, okay, or potassium tartarate. Now such crystals, as you can see, they are looking different and they are almost like as if they are mirror images of each other. Okay, I mean A, the crystal form, is a mirror image of crystal form B. So what Louis Pasteur did was he handpicked using forceps the crystal form A and crystal form B and separated them. And then he passed this plain polarized light through these crystals, and he could see that the crystal form A was able to deflect the light by an angle theta, where the crystal form B would deflect the plane polarized light by an equal angle but in the opposite direction. Now, he wanted to see if he could mix equal amount of A and B and put it inside a solution, say in a 50-50 ratio, and then if he passed, so this is the solution of A and B, and then if he passed the plane polarized light, would he see any deflection? But there was no deflection obtained over here. That means we are not seeing any optical rotation for a solution having 50% of A and 50% of B. This type of a solution which is having equal amount of A and B and has no optical rotation was called as to be a racemic mixture. However, when he took a separate solution only having A and only having B, and then he passed light through it, so now we are not considering any crystal over here. We are thinking the compound A to be at the molecular level. So now he wanted to see if at a molecular level these crystal A or crystal B were able to deflect a light, and what he observed was that it could deflect the plane polarized light again. So this is my plane polarized light, and solution A, let's consider deflected the light to be in the plus phi direction, and the solution B deflected light in the minus phi direction. Okay, that means deflection at equal angle but in the opposite direction. So these type of compounds A and B were then called to be as, by Louis Pasteur, he defined them to be as enantiomers. So he said that compounds initially which were crystals that are non-super imposable mirror images of each other are called enantiomers. Okay. Now here the compounds that we are talking about, okay, they also can be gases, liquid, or molten or solution. That has to be kept in mind. Okay. This rotation is observed and measured by an instrument called polarimeter. Okay. So in this particular polarimeter, the important point to remember is that a sodium lamp is used, and which has a wavelength of around 589 nanometer. This has to be kept in mind. Now, what are the factors on which the optical rotation depends? So let's say factors on which optical rotation depends are going to be following: sample concentration that we have taken, and that is expressed in gram per milliliter, the temperature at which the experiment is being conducted, the solvent that has been used, the wavelength of light, that means the light source itself. Obviously over here we are using a sodium vapor lamp, and E, the tube length, which we measure in dm. Okay. So the specific rotation over here, let's write the observed rotation over here is actually proportional to the, because temperature we are conducting at a fixed temperature, solvent we are not changing, wavelength we are not changing, so it will be dependent on the concentration and the length of the tube. So we can write that the observed rotation will be alpha specific C times L, or the specific rotation will be alpha observed divided by concentration and the length of the tube. Okay. Now, Having said this, we can do some problems regarding the specific rotation. So what are these problems? Let's have a look. Okay, it is worthwhile to mention over here that each enantiomer that we were discussing, okay, these enantiomers, they have same physical property. Example, the melting point, boiling point, and solubility, with only one exception, that they rotate the plane polarized light in opposite directions. Now, enantiomer that rotate the plane of light to the right, which means clockwise, they are called dextro-rotatory, and the symbol given to them is small d, whereas if the plane of light rotates left or counterclockwise, they are called labiorotatory. And the symbol given to them is small l. Okay. Now a solution, as I had said before, when they contain equal amounts of dextro and labiorotatory, they are called as to be racemic mixture. Now, when one is present more than the other, then we call the solution is having enantiomeric excess. So when we say enantiomeric excess it means one enantiomer is present in excess over the other. Now the percentage of enantiomeric excess, how to measure? For that the formula is enantiomeric excess number of moles of enantiomer A minus number of moles of enantiomer B divided by number of moles of enantiomers. That is what it means. So for example, if we say enantiomeric excess of 50%, this signifies, इसे हम लोग क्या समझेंगे, that the sample contains 75 enantiomer say R, which is the absolute configuration, and 25% of enantiomer say S. Okay, this is what it means. So a racemic mixture will be ideally what? 50% of R and 50% of S. A racemic mixture will be 50% of R and 50% of S. Okay. Okay, let's do some problems regarding optical rotation. So the first problem given over here is, say, suppose a 1.20 gram sample of cocaine the alpha D is given to be minus 16 was dissolved in 750 ml of chloroform and placed in a sample tube having path length 5 centimeter. What is the observed rotation? We got to find that out. So how to do such a problem? कैसे करेंगे? So alpha d माने specific rotation. हमें क्या पता है? It is alpha observed divided by L into C. और फिर लिखेंगे क्या? Alpha observed हमारा क्या है? L into C into alpha d, which is my specific rotation. Alpha d जो है -16 दिया गया है. L 5 सेंटीमीटर है जिसको डेसीमीटर में लेके जाना है. So we will divide this by 10. So this will be your length. Concentration हमको ग्राम पर ml पे लेके जाना है. So it will be 1.20 gram divided by 7.50 centimeter cube, or we will say 0.60 gram per centimeter cube or ml, the same thing. And if we now do the math to calculate the alpha observed, -16 into 0.500 into 0.16, so the solution will give us the answer to be as -1.3 degrees. Okay. Now in another problem, we have been given, supposed to find out a 1.5 gram sample of cocaine, the toxic extract of poison hemlock was dissolved in 10 ml of ethanol and placed in sample cell with 5 centimeter path length, the observed rotation at sodium D line was plus 1.21 degree. We got to calculate alpha d, which is my specific rotation for the cocaine. So for that, what will I do? I know that alpha specific rotation is nothing but alpha observed divided by length of the tube and divided by the concentration. So out here concentration will be 1.5 gram divided by 10 ml, which means 0.15 gram per ml, and length of the tube has been given to be as 5 centimeter. So this will mean 0.5 decimeter. Now if we calculate divided by, okay, so if you do the math over here, you will get the value in the positive, and that should be coming out to be as 1.21 divided by 0.15 divided by 0.5, that is 16.13 degrees. Okay, so that is how we have to solve these problems. Okay, so in this particular problem, they have said when 0.575 gram of monosodium glutamate, which is MSG, is dissolved in 10 ml of water and placed in a sample cell 10 centimeter in length. Okay, so we have the volume being given to us, that is 10 ml of water. The length of the tube is given to us. The observed rotation at 20 degrees centigrade using a D line. D line obviously is that 589 nanometer, and that is given to be as plus 1.47. We have to calculate the specific rotation of the MSG. So that is what we need to find out. What is the formula? We know that specific rotation, which is this one, is observed rotation by L into C. Okay. And what is the observed rotation given to us? 1.47. That also in plus. What is the length of the tube? 10 centimeter. In decimeter it means what? 10 centimeter in decimeter means 1 decimeter. So it is 1, and divided by what? Concentration is what? 5.575 gram. What is the volume? It is 10 ml. So that means it is 0.0575 gram per ml. And that is, and that if we calculate will come out to be plus 25.56 degree. Next problem, when 1.35 gram of menthol dissolved in 5 ml of ether placed in a sample cell 10 centimeter in length, the observed rotation that we find is this much. We have to calculate the specific rotation again, just using the same formula. which is alpha D, alpha observed, L into C. What is the length? 10 centimeter means 1 dm. What is the concentration? 1.30 gram divided by 5 ml. Okay. So that is 1.3 divided by 0.26 gram per ml. We just need to plug in these values. So we will have plus 0.57. That should be divided by 1 dm into so that comes out to be plus 2.19 degree. That should be our answer. Again, a similar problem has been given over here. So I would request you to try this out at home. Okay, so we have now a problem which is related to enantiomeric excess. Okay, and we have to find out a method to solve this problem. Okay, so it has been given to us what? A specific rotation of a optically pure. Okay, this word is important. Is this? A chemist devised a synthetic route to prepare optically pure adrenaline and it was suspected that the product was contaminated with small amount of undesirable enantiomer. The observed specific rotation, okay, was found to be this. So your enantiomeric excess, which is percentage EE, is nothing but observed rotation divided by the alpha value for pure enantiomer times 100, which means now 45 divided by 55 into 100, and that would give you 85%. So out here, this is indicating what? This is indicating that 85% EE of adrenaline is pure enantiomer, and 15% is the racemic mixture. So this 15% is what? 7.5% of adrenaline and 7.5% of is enantiomer. Okay. So this is the DL part. Okay. So this means, in other words, the total product has 92.5% of adrenaline and 7.5% of the undesired mixture. Okay, that is what it means. Let's go for another problem in which it has been given that the rotation of L-DOPA in water is minus 39.5, and the chemist prepared a mixture of L-DOPA and its enantiomer, and this mixture had a specific rotation of minus 37. We have to calculate the percentage of enantiomeric excess, which we will say again observed alpha divided by alpha of the pure enantiomer times 100. So this is minus 37 divided by minus 39.5 into 100, and that would be around 93.67% of enantiomeric excess. Okay, so that is how we need to calculate and solve these type of problems. Thanks for listening. Have a great day.